Okay, hi everyone. Thanks for those of you coming in person. So today I'd like to introduce Victor Robles, who's visiting us from Yale. So Victor's, I can see you're a research associate there or a postdoc or something.
I'm a YCF fellow.
Okay.
Yes.
So Victor's done a lot of work on basically probing dark matter physics using cosmology and galaxies and things like this. So Victor's visiting us until the 21st. And are you in Ellen's office or are you down the hall?
I'm down the hall.
Okay.
Shirley.
So down at the end of the CIFA corridor by the printers, you can go and visit Victor if you have more questions. But for now, I'll leave you with in Victor's hands for your seminar. So thanks, Victor, and take it away.
Thank you. Thank you, Darren. I'll try to actually move myself in this way so that you can see the screen. Hopefully, it will be better for you. Try to move it around this way. Well, yeah. So thank you again for showing up, and thanks for those of you who are on Zoom. So part of the work that I'm going to talk to you today is part of the collaboration that I've been doing with the FIRE collaboration, which is a group that's working in different places basically, and these are some of the universities where the people are working on, but there's other people working in different places. And so I'm going to talk to you a little bit about the things that I've been doing in relation to dark matter and how to use this local group observations to constrain some of the properties of dark matter. And by the way, so I said I'm current fellow at Yale, and but next year I'm moving to Rensselaer Polytechnic Institute as a tenure track faculty. So, okay, hopefully that works. Okay, so let's start. So one of the things that we know from, put this out of the way. So one of the things we know from observations is that we have information from different parts of the universe as it evolves. And one of the things that we want in the next couple of years is to get a better picture of how this works. And by that, I mean, getting more observations specifically of how galaxies evolve from the early times all the way to today. One of them is going to be James Webb Space Telescope is going to tell us about the early stages of galaxies. And one of the things that we want to understand when we do galaxy formation is how these galaxies started from, let's say, the initial condition, which I'm going to say it's cosmic background. So like these early fluctuations in the universe, how they grow all the way to today. And by that, it means going from these early fluctuations all the way to the distribution of galaxies that we observe. Now, of course, when we look at the sky, we see different times. So these are snapshots of times that we have to stitch together to make a consistent picture of how these systems evolve. But a way to do it in human life, in human lifetime, is to something I call just time machine. So in other words, what we do is we use our physics laws and we put them into a computer from our initial condition, and then try to evolve them all the way to today or different times and see how well our models match the observations. And the reason why we do this is because, again, we don't have an infinite amount of time or infinite number of people. So we have to fast forward the evolution and see, how much we can learn from our simulations or like these physical laws and try to modify them accordingly to the observations. So as you know, there's a lot of observations that we've gathered through a number of years that we have this telescopes going. But one of the things that we want to explore further is not only looking at galaxies nearby. So there are surveys that are coming next decade, and I just mentioned here one. So DESI, as I said, it's one of the things that is ongoing, it's ongoing and it's taking data. And the thing here that we want to explore is going deeper in redshift. So that is, we want to understand how galaxies are forming, as I said, in the very early stages of the universe, to map their structure all the way to today. And this is because we not only want to reproduce the universe that we observe now, we want to know how this universe was evolving through different times. And so the next couple of decades, the next couple of years and next decade at least, there are going to be a lot of these observations telling us more and more about the early universe. Now, these are observational motivations of things that we will like to compare with. But going back to our models, one of the things that we know, or at least is the current understanding of the universe in terms of the contents of it, is that we think that there is a some form of matter that somewhat brings these structures together, and that is called some form of dark matter. And the standard model of what this type of dark matter could be is something that is a collisionless particle of very massive type, and essentially that is that has a very weak interaction, and that is going to add to 27 or 26% of the total mass in the universe. There is another component that is what we actually observe, that is the stars and gas and all the other elements. And one of the things that we think is that this only comprises about 5% of the matter here. And the rest is something that we just call dark energy, which I'm not going to talk too much about today, but it is some form of energy that will be responsible for the expanded or the accelerated expansion of the universe. So if we go back to the dark matter, so one of the things that we know is, in fact, that we just don't know what dark matter is. And there is a range of parameters, of parameter space here that it hasn't been explored. And here is not an exhaustive list, of course, but this is just to show you that there are a lot of models that we've been trying to come up with in the last couple of years to understand what kind of properties in dark matter could reproduce these observations. So the WIMP, or the standard cold dark matter model, somewhat lives in this high mass regime. But there are other models, such as Born dark matter or self-interacting dark matter, that will change the dark matter properties. And one of the things that we want to understand from astrophysics is how to constrain this parameter space to narrow down the range to more viable, parameters that we can further explore with either experiments on Earth or more detailed detectors. So because this is a huge parameter space, astronomy, or at least astrophysics, has the potential to narrow down these windows of viable dark matter candidates. So I'm going to talk about specifically about some of these candidates and how we can constrain them using local observations. As we know, there's with these simulations or this type of cold dark matter simulations, one of the things that we can do is, as I said, put our physics in our computer and evolve the system and see, what does the universe looks like in our computer. And one of the things that we find is that there's a lot of these structures that is found in this cosmological cold dark matter simulations. But one of the things that we know is that when we run simulations, we can do actually something else that we call a zooming technique. So some of you may be familiar with this, but essentially the idea here is that you can take patch of the universe and then simulate that patch with much higher resolution in order to resolve what will be the structure at much smaller scales. And the reason of that is because we want to compare not only with the big volumes, but also with the smaller volumes, because we have observations at also different scales. So one of the successes of the model is that we can recover these cosmic webs, distribution of structures. But here what I'm showing is the numbers on the y-axis is, you can think of this as the relative number of structures that are in the universe. And then on the x-axis is the mass of the structure. Well, in the magenta stars, what you observe is the number of galaxies that we observe. And what you see here is, that there is some, actually it's hard to see with this projector, but there is some gray band here that will basically tell you that we are incomplete in this regime. And the reason is because on the low masses scale, because these galaxies are faint, we don't really have enough observations to constrain too much what will be the slope of the luminosity function. On the other hand, we have this black line here, which is the number of structures of dark matter in the cold dark matter scenario. And what you observe here is that you have a lot of them at pretty much all scales. Now, one of the things that we do as astrophysicists is try to use a different way of rephrasing this in a more familiar way, and that is through some sort of abundance matching technique, in which we basically put this galaxies that we observe into the dark matter halos that we have in our simulations. And then we come up with something we call the stellar halo mass relation. So what this plot is telling us, roughly speaking, is how to locate a galaxy, for instance, the Milky Way, in that it has some given number of stars that we observe into its dark matter halo. So this way, for instance, for a dark matter or for a Milky Way galaxy, what it will say is that given the number of stars that we observe, then it will probably be living in a 10 to the 12 star mass halo. So in this way, well, one of the things that we can observe is that although there is some scatter, because of course we have millions of galaxies out there, when we go to the low end, that is galaxies that are below 10 to the 7 in stellar mass, they will roughly be living in halo mass of 10 to the 10. But this is where our observations are limited. And they're limited again because these are faint systems, so we don't have enough of a big sample to begin with. So most of these systems can be observed only within the local volume that is nearby. And this is the regime where we actually want to push, more observations on in order to constrain this scatter in the low mass end. So just to give you a sense, for instance, what you can do with dark matter with this type of observations. So one of the things that happen, for instance, in the warm dark matter scenario is if you assume that the particle mass is not 100 GeVs or very high mass, but instead you assume that this is a smaller mass. So for instance, here, 1 keV. What happens is that you effectively have some free streaming lag. So that is, for a smaller mass particle, you have that some structures will not be formed below some mass scale. So what that means is that below some scale, presumably the smaller scales, is where you're going to start suppressing how many of those structures can form. And you can see it here, for instance, on your right side, you have a cold dark matter simulation, which is this collisionless particle. And the warm dark matter that is slightly, this is much smaller mass. And what you hopefully can observe is that there is much smaller structure in this region of space, whereas the most massive halos that like here, A, B, C, they actually form. And one of the things that you can do with that is that if you go back to, again, like this plot of relative abundance of structures, what you see is that the effect of the dwarf dark matter will be that instead of having a black line here, like the cold dark matter, it will have a roll-off, which basically we mean, what we mean by that is we'll have some suppression of structures below some scale. That means that below some scale, you're not going to have too much dark matter halos. So you can play the game up to different masses for dark matter. Here's shown 1, KD, 3, and 10. And one of the things that you can already see is that if you go too low on mass, so like below, let's say 1, at some point you're going to be below the magenta point. And what that means is like you're not going to have enough dark matter structures where the galaxies will live. So that is, you're not going to have enough hosts for the number of galaxies that we observe. So that means that you at least need about the same abundance of galaxies as dark matter halos. So this already puts a bound for these type of dark matter models. Roughly speaking, your conservative will be around 1, or if you want to push a little bit more, you can think of somewhere around a bit larger than 1 keV. So clearly, the dwarf galaxy observations are already telling us, we need something on order larger than these masses. Now, as I said, because of the numbers and the limiting luminosities of these objects, the faint galaxies, we try to explore in more detail these observations, these galaxies, and the way that we do it is, again, in the local group. That's where we can observe these systems. And the local group, just to give you reference, I know you already know this, but just to refresh your memory, essentially is made out of the Milky Way, Andromeda, and the galaxies that are in between. And these galaxies, as we know, these are satellite systems, so these are much smaller masses. But just to give you a sense of their order of magnitudes, for instance, Milky Way and Andromeda are roughly a few times 10 to the 10 solar masses. For the most massive satellites that we have for the Milky Way is the Large Magellanic Cloud, which is a few, 10 to the 7, 10 to the 9 solar masses around that regime. This is what people normally refer to as bright dwarfs. And then there is like these other dwarfs that we're going to call classical dwarfs or ultrafaints, which are roughly in the regime of 10 to the 4 to 10 to the 7. And as you can see, they have less of a very nice shape. They actually, some of them are actually hard to see here. But these are the most important regime that we think that can tell us more about dark matter. So just for the sake of definition, so anything that is less than 10 to the 9 in stellar mass is what I will be referring as a dwarf galaxy. So as I mentioned, the dwarf galaxies in general are quite important for dark matter because they're faint systems. That is, they have low number of stars. And we think that their stars is going to be mostly tracers of the dark matter. So one of the things that people have mostly worked on is to constrain where the most of the stars are. And we kind of parameterize that by some effective ratings. So that is like how compact these systems are. But there are some now new attempts that people are trying to pursue in going farther than this effective radius. And one of those initiatives is, for instance, using the prime focus spectrograph, in which basically the idea is, as I'm showing here for 4NETs, is to go beyond the half-light radius and actually start mapping more of the galaxy itself. And the idea here is to go to see, what will happen in the outskirts of the galaxies and try to constrain what is the dark matter distribution, not only where most of the stars are, but also in the outskirts of that. So this is going to be quite interesting because this can tell us, as I mentioned in a couple of minutes, something more about the whole density profile for the dark matter in these galaxies. So for instance, in cold dark matter, we know that if we look at the structures at these individual halos, we have a very characteristic shape for their density profiles. So here on the y-axis in this plot, I'm showing the dark matter density and the radial profile. And here is the distance with respect to the center of this galaxy. But one of the things that we know from simulations is that we can parameterize the dark matter component by the somewhat well-known profile called Navarro-Frank-White profile, or NFW, which has this characteristic inner behavior in the density that goes like 1/r. And this is colloquially referred to as a cost profile, given because by the fact that this is a cost or divergent type of density. And one of the things that that happens when you do the comparison, for instance, with coupled dwarf galaxies and this dark matter model, is that instead of actually following, for instance, this cost profile that will translate to a rotation curve, which is like the circular velocity of stars in the galaxy like this, it will be roughly this dashed line here if it is an NFW profile. Now, as you can clearly see by the dots, this is a dwarf galaxy, this is DDO 43 or 126. And you can see that these galaxies seem to be more consistent with something that is, in fact, what we say a core-like. In other words, that the density profile seems to be shallower at the center. So because we actually have these type of galaxies, there seems to be something that we need to do in order to reproduce, galaxies that are core-like. Now, it doesn't really mean that there are no cost-likes. In fact, this has been debated by, many groups and many years. But now it has to learn a little bit in the sense of how to recover this diversity of galaxies between core and cos within a single dark matter model. The other thing that is interesting, that is somewhat of a also debatable tension, is that if you look at the structure of Milky Way, you see, for instance, here, one of those simulations of a Milky Way halo, and you count the number of structures, for instance, the most massive objects that you form, so the brightest systems that you can see here in this plot, and then you compare it with, let's say, the brightest systems or the brightest galaxies in the Milky Way. And when you do the matching, what will happen is that even with the current counts, which has actually added up a few numbers, you still have much more structures in the dark matter simulations than what you observe. And here's what is basically shown. So the dashed line or the solid line here is the number of structures that you will see according to some circular velocity. You can think of these as increasing mass or smaller masses this way. So many of the small structures here are formed in the simulations, as opposed to this green, the triangles here, which are basically the number of structures that we observe, the number of galaxies that we actually see. So we can see that there is also some discrepancy here in terms of the numbers, but you can always say, well, with the new telescopes and the new surveys, these numbers actually have increased dramatically in the last couple of years. And this is just the number of satellites that we have been discovering the vicinity of the Milky Way. And thanks to these new instruments and cameras, we actually have detected more and more potential candidates. So in the next couple of years, this is something that we will be able to answer in somewhat a more solid, with a more solid, I guess, argument to see how many of these systems actually are out there, and if that is consistent with the type of predictions for cold dark matter. In a related, I guess, in certain spirit, it's a similar problem, but it's slightly different in the sense that if you look at the dark matter simulations that I showed before, and you look at the most massive objects that you form, such as what I mentioned in the beginning, then if you look at the density profiles or like circular velocities for each of those systems, you will have, for instance, one of these lines. So all of these lines is one dark matter structure that you form in your simulation. If you compare it with the brightest systems that we observe in the Milky Way, so these are the points here, the classical Milky Way dwarf galaxies, if this was a one-to-one match, you will only see 9 lines here crossing the points. But obviously you see more of these, which means that we have more structures, which we know. But there's also these lines that are above any of the points. And this means these are objects that are way too massive. These are like, massive dark matter halos that unfortunately do not have any counterpart that is observed. That is, we don't see that many bright galaxies in the Milky Way. So if these systems do exist, then we should actually see their galaxies. Unfortunately, we don't see them. So this is also another discrepancy that's been lingering there in terms of the cold dark matter simulations. So hopefully, I just try to motivate a little bit that there is in fact some tension, let's say, or some discrepancies, maybe not tension. Some people may not think that this is a tension, but let's just call them discrepancies that somewhat motivates that there is new physics or some physics that we have to add that doesn't really come from dark matter only, at least not from the cold dark matter. So there are two approaches to actually reduce these tensions, and one of them has been historically working on the 5% of matter that we actually observe. And that is, all this dark matter physics can be complemented with the rest of the hydrodynamics, which happen at different scales. So how stars form and how this affects, the scales of from giant molecular clouds all the way to dwarf galaxies, Milky Ways, and much larger structures. So there is a huge community, and not only from FIRE, but here I'm just listing some of them, working on different scales for the astrophysics and see how that affects these different scales and see if we can actually match more and more of the observations. There's another approach, and that is, instead of actually taking more of the weight on the astrophysics side, maybe the way to tackle these tensions is through the dark matter component. So in fact, if we can change the properties of dark matter, which we just don't know what it is, as I said, but we try to change it to something slightly different, then perhaps we can reach a better agreement without doing any a lot of fine-tuning or crazy physics here. So of course, we don't have to neglect this, but we know that they exist. But this type of solution, what it means is that we're going to approximate more of the observations with just dark matter physics. So I've been working a lot on this type of approach, and in fact, I'm going to talk about more on this side. And one of the candidates that I've been working on in this spirit is basically changing the dark matter interactions. So if you do not assume that this is a collisionless particle, so let's assume that now it has some strong interaction in the dark sector. So what that happens, what that implies is roughly that you will have some scattering rate between these particles. And the important part of this, or the important effect that comes from this new physics, is that the scattering rate will actually change some of these predictions from cold dark matter in the regimes of dwarf galaxies and the central parts of galaxies in general. So the important or the relevant parameters is essentially that the scattering rate will be depending on the central dark or the local dark matter density and the relative velocity interaction. And then these parameters is basically a cross-section of the mass. And this is the part that we can actually constrain with the astronomical observations. So if you plug in a little bit of the dwarf galaxy scale numbers, then you roughly come up with a factor that is sigma over m of order 1 centimeter squared per gram. That's where you start having some interesting effects on the dwarf galaxy scales. And just to give you a sense, the cross-section that we're talking about with this type of dark matter model is basically on the order of nuclear scale. So if you compare that to those cold dark matter, the standard WIMP, this is orders of magnitude actually stronger than that. So the other one is more in the weak scale. So this is actually quite different. So what is the effect for the dark matter profiles, for instance, when you add self-interactions? So here I'm just showing what is the density profile for different cross-sections of a typical dwarf galaxy halo. So for this, you can see the blue line is the cold dark matter, and the case of which is this typical NFW profile. So if you add the self-interactions, what you see here is, for instance, how you can start developing a shallow profile of the center. And what the physics that's basically behind all this is that because of the self-interactions, what you're essentially doing is they're thermalized in the inner parts. Because the self-interactions will have a more larger effect where the density is high, as I mentioned, because they have a large scattering rate. So then mostly of these effects will be happening, will be changing basically in inner parts of the galaxy. And as you can see, if you go to very large cross sections, then at some point it becomes rather hard to disentangle these numbers. But there are other ways that I will mention in a couple of minutes or in a couple of slides of how you can actually constrain the upper part of this range of cross sections. So in this spirit, we can recover some cores. So this is going in the right direction, at least to match these dwarf galaxies that have score-like behavior. But of course, you can now ask the question, how much of these dark matter physics will change once we go to the whole astrophysics? Well, this is kind of this one of the work that we did a while ago. And this is actually a set of so many simulations that we run with the FIRE astrophysics in both cold dark matter and self-interacting dark matter. And the idea here was to look at what is the type of galaxies that we form within a Milky Way, within a dwarf galaxy dark matter halo. So all of them are roughly 10 to the 10 solar masses in dark matter. But as you can see here, we have a different number of stars according to like the different systems that we have evolved. So one of the things that you observe from left to right is that you have low number of stars from the left all the way to 10 to the 7th on the right. And the thing that you observe, first of all, sorry for that, is that if you look at these profiles, which is dark matter density profiles, if you look at the solid lines, this is the cold dark matter simulation. The thick one is with the astrophysics, so the whole FIRE physics, and the thin line is without any astrophysics, just dark matter. And what you observe from left to right is that these lines are basically tracing each other, except at in the higher mass systems, then they start diverging. Basically, you start forming a core. If you redo the same simulations, except that the dark matter physics is different, so changing the cold dark matter to self-interacting dark matter, then you will see the same line. So the thick one is with the hydrodynamical FIRE physics, and the thin line, thin line is the one without any astrophysics, just self-interacting dark matter. And from left to right, you see that both lines are kind of close to each other, even though you actually have orders of magnitude difference in the stellar mass. So one of the things that this is telling us is that dwarf galaxies in self-interacting dark matter, even with the FIRE physics, they're actually much less sensitive to all these processes are undergoing, in particular the feedback. So you can actually think of these a different way. And if you go to the very central parts of these galaxies and ask what will be the inner density slope of the density profiles, what you will observe is that there is in fact some strong trend of forming cores in cold dark matter simulations as you have larger and larger stellar mass in your galaxy. And that means you have enough feedback effects or some strong impulses due to the feedback that you actually can remove some of the dark matter from the inner parts to the outer parts. So that basically transforms your inner cosm to a core. However, you look at the self-interacting dark matter, you actually see that even with the same FIRE physics, you actually have a very small effect due to the whole hydrodynamics feedback. And the reason of that is, again, because the self-interactions already thermalized inner cores. So if you pump more energy with the feedback or winds or whatever the astrophysics was doing, you cannot really have too much of a damage to the inner parts because you're already hot, you can say, in that part. Now, there is some slight trend of going to, say, a mild cost or positive region in this plot as you go to smaller and smaller galaxies. And the reason of that is because the scattering rate will become smaller. So then that means that in this case, since we're looking at 250 to 500 parsecs, which is roughly the sizes of galaxies that we observe in the classical Milky Way dwarf galaxies at least. So what this essentially means is that the cores are going to get smaller than this radius. It doesn't mean like self-interacting dark matter doesn't form cores. It just simply means that as you go to smaller and smaller scales, your cores are going to become smaller. So this is a way to summarize. Well, colors are kind of interesting here. It's not what is shown on my screen, but anyway, the point here of this plot is to kind of summarize the effects of feedback, as I mentioned. In the y-axis is basically the cos or core transformation. So anything that is on the upper part to close to zero is more like a core, whereas going to a cos is something more in this blue line that says NFW. So as you can see, all different groups, not only FIRE, this is just showing different astrophysics from other groups. And all of them seem to somewhat converge to the fact that in the limit of bright bursts, so roughly speaking, galaxies that are 10 to the 7 to 10 to the 8, they tend to actually do well into transforming a cos to a core, because again, you have enough stars to do the damage in the inner parts of the galaxy and remove some of the dark matter. But as you go to lower and lower massive scale, so roughly a few times 10 to the 6, at least that's in FIRE, so then this transition becomes actually sharper. And then it turns out that most of these galaxies, even with the fire astrophysics or any astrophysics, they actually return to a cosmic profile. So this is quite relevant because if you look for the dark matter physics that it comes from self-interactions, for instance, then that means that even in this limit, you should expect some core-like profiles. So this is something that, worth paying a little bit of attention, because the internal structure of these galaxies could tell us more about dark matter physics. On the other hand, we have the superstructure. And what I'm showing you here is basically two simulations, cold dark matter simulation versus self-interacting dark matter of the Milky Way galaxy halo. And this is a very crude way of putting it, but essentially this is just this galaxy, the center, means that we are taking into account the effects of the Milky Way baryonic component. That means that we actually put the bulge, the disk of stars, the gas. And the effect of that on superstructure is basically shown here. On the y-axis, you have the numbers of halos versus the radial distance with respect to the central part of the galaxy. And one of the things that you see here is that the cold dark matter case is this black line here. You have, of course, as I mentioned in the beginning, hundreds of these systems of within the virial radius. Now, if you look at the self-interacting dark matter, is this red line here with a cross-section of 1, you see that even if you can form cores for their, few parsecs, as I mentioned, for the structures, the individual structures, you see that in terms of superabundance, it roughly gives you about the same number as cold dark matter. So whatever to be, okay, I'll go to that in a minute. So the other thing is, if you increase the cross section, so same self-interaction but just larger cross section, then what happens is that you have this blue line here. So you can see that by comparing the red line to the blue line, you're shifting the number of structures down. That means that you're suppressing more and more of the structures that can form. That is in fact relevant because if you look at the number of Milky Way satellites that we know, this is the green line. So you can see that the blue line actually in radial space, in radial distance, you can already see that this is basically below the galaxies that we see within 50 kiloparsecs. Now, of course, if you just look at the total abundance, then we still expect more and more of these structures. Now, it is possible that, as I mentioned, that if we find more superstructures with the new surveys out there, then this green curve would actually shift up. Now, how much? Well, this is to be seen. But the important part that in terms of self-interacting dark matter is that if you keep pushing this to larger and larger cross sections, you already see that then this is going to start becoming a problem, because now you're going to start suppressing more and more structures. And within this 50 kiloparsec regime, we think that we are somewhat complete. That means that the galaxies that are out there, we should have already seen some of them, or most of them. So it means like we actually have to get the blue line closer to the green line, not the other way around. Now, if you look at this individual structure, so this is work from PhD student and Irvine, and basically what we did here is we'll look at this same simulation, but now look at the individual structures of these dark matter halos. If you compare them with the local observations, again, the Milky Way dwarfs, which are basically these black points, you see that you always have halos that will accommodate those structures in cold dark matter. And the green points are actually ultra-faint dwarf galaxies that have been recently discovered. So the uncertainties there might be somewhat, may change in the future, but let's just take that for granted for now. And if you can see here, there's always halos, as I mentioned in CDM, where you can host these galaxies in. And of course, you also have these too big to fail problems. You also have some massive halos. Now, in self-interacting dark matter with cross-section of 1, what you observe is, again, you have the score-like profiles for the bigger halos. And if you have cross sections of order 5, then you actually still have the core halos. But one of the things you notice is that there's this lingering population of green points that are actually above any of the halos that we found. So in that sense, what we're finding is that in self-interacting dark matter, at least with this type of cross section that is velocity, is velocity independent, so it's a constant cross section, it is going to be kind of hard to actually recover now compact and dense structures if these are actually there. So then the problem here is how to recover, again, this diversity of structures within even the Milky Way. So now we are consistent with cores, but now we actually want to get back to a little bit more core-like or dense systems even Milky Way. So again, if you just look at all these different constraints from the internal structure and the abundance, you can already see that it's roughly about 0.5 or 3, within that cross section over M, this regime, this is where you can actually expect to have some difference or still viability for these type of dark matter to be consistent with these observations. So in that sense, this is a very narrow range in the parameter space that I showed at the beginning, because this is already quite constraining. Now there is other scale, so this is only local group observations, but of course there's a way out, let's say, if you want to complicate things a little bit, and that is if you add the velocity dependence, and the reason of that is also motivated by the cluster scales, although I just learned that there might be some wiggle room for the cluster scale to actually shift these values up. But one of the things, at least for local group dwarf galaxies, is that if you had some velocity dependence in your cross sections, then you can have some core collapse for some of these structures. So that means that your dark matter structures will start forming cores, as I mentioned in the beginning. But if they, by some effects, they start getting denser and denser, then they will undergo core collapse. And what that means is like their inner density profiles is going to be hard here to look at, but in the movie, what you see, hopefully, is that you form a core, but if you let the system relax, then if it can get too dense because of tidal stripping or other effects, then it can actually become a very compact and dense system. So this could actually be a way to form these little ultra-faint galaxies that I mentioned. Now, we are exploring whether this could be some way out to have this diversity, but this is still under exploration. Now, the other model that I've been working on, and this is actually quite a more recent one in terms of the work that has been done numerically, is this is the so-called ultralight scalar field dark matter, or some people might know it as fuzzy dark matter, wave dark matter. Essentially, all of them are different names for the same model, which basically is scalar field dark matter. So the basic idea of this model is that if you go all the way to the low mass particle, and so of order 10 to the minus 22 EVs, then if you compute the de Broglie wavelength for that mass, then what you end up having is that you have of order kiloparsec scales. So that means that you can have some quantum-like phenomena in that sense at the macroscopic scales, basically at the scale of galaxies. So what this means is that your field is going to behave as a coherent field on the scales of kiloparsecs. So when you run a simulation, and this is kind of one of the things that I'm showing here, what you observe is that there are different phenomena that you actually have that you don't have in self-interacting dark matter or cold dark matter. And one of the things that you find in these systems is that your systems or your virialized halos are quite unique in the sense that they have a very complex object at the center, which instead of being an NFW profile, it has a profile that we just call the soliton profile, which is essentially a core-like profile that has a core and then it has a steep transition. And then in this surrounding of that very complex source, you have the whole dark matter that is fluctuating, because this behaves somewhat more like a field. So what you have is just a dark matter field that is fluctuating, and as you average out, this sort of fluctuations, let's say spatially, then kind of it goes as asymptotic NFW profile on the outskirts. So mostly the difference is going to be in the inner parts where you have the soliton. Now, one of the things that you can do with that, again, is that now it's different dark matter physics. The physics that is at play here is, again, this quantum-like pressure. And then what that is going to do is, again, is going to suppress the structures that you can form below some scale. So in the same spirit as we did in coherent dark matter, so this is going to have some roll-off in the number of structures that you can find, depending on the mass of the dark matter particle. And here I show different boson masses and where the cutoff is. And you can already see that if you go too low, so for instance, 10 to minus 24, you have this red line here that is clearly not enough to host the number of galaxies that we already observed, like even the Milky Way, for instance. So then if you can just, if you're conservative, you can think of having a lower bound that already tells you 10 to the minus 23 or lower will be ruled out. So on the other hand, what we can do with dwarf galaxies is try to constrain this parameter a little bit more. And if you look at the density profiles for dwarf galaxies, for dark matter halos, in the scale of dwarf galaxies, then here, this is what is shown. You have the dark matter or cold dark matter, which is this black line here. Then the dashed line is the self-interacting dark matter that I've been talking about with cross-section of 1. And then there are two magenta lines, and for two different boson masses in this model. So when we normalize typically the mass of dark matter in terms of 10 to the minus 22 EVs. So for M22, which is the solid line, the magenta solid line here is for 10 to the minus 22 EVs. You have this density profile that is shown basically the soliton. And then if you have a factor of 10 larger mass, then you have a more compact and dense soliton in this central part of the halos. So one of the things that is important is that we have observations in this regime that is shown here in the shaded band for the Milky Way dwarf galaxies. So one of the things we can do is ask if all these Milky Way dwarf galaxies are in fact living in solitons, then what will be the density profile? Will it be a core or a cusp? And this is what is shown here. On the y-axis is the inner density slope at the typical size of those galaxies. So you can think of this as the effective radius or the Havlik radius. And what is shown here is for two boson masses. So for instance, in the dashed line, the black dashed line, here are the 9 most massive dwarf galaxies. So each point is a galaxy. And what is shown here is that all of these galaxies will be having a slope of close to 0, so like core-like profiles. And the reason of this is because they will all be living in their solitons, essentially, the inner part of the soliton. As you go to 10 to the minus 22, which is this black dashed line here, what you observe is that galaxies that are compact or smaller, they will preferentially be core. So that means that they will be living in the inner parts of the soliton. But as you go lighter to larger galaxies, then they are going to have something more of a cuspy profile. So you can already see that there is some diversity that turns out from just dark matter physics. Now, so one of the things that we can ask is, of course, what will be the effects for once you put the systems into a Milky Way? So these are isolated objects. We found what is the behavior of the inner solitons. But if we actually do this game of what will be one of these halos as it evolves in a Milky Way. So this is a semi-analytical model for that. So this is only taking into account the tidal field in a semi-analytical way. And one of the things that these authors found is that in this type of dark matter, scalar field dark matter, what they found is that most of the mass that is stripped by the tidal field is in the outskirts, as you expect. But what you see is that the soliton is quite robust. So in this plot is basically showing the density as it evolves for different times. And you can see that the inner soliton, which is this overlapping of the curves, is quite robust to this tidal disruption. So this is quite interesting because it means that these structures, even if they're compact, they can well survive the tidal field. Now, another thing we're doing is exploring this interaction of stars within the solitons. And this particular case, here it was work from one of the students at Yale, has just graduated, in fact. And what he was doing is basically looking at just one compact source. So a very, you can think of this as a stellar cluster, nuclear cluster, or even a black hole, depends on the type of analysis. But the point here was to look at a very compact source at different masses as it evolves within a soliton. And what he found essentially is that if you start at the center of the soliton, because of these quantum field fluctuations, the soliton actually oscillates in time and space. And that oscillation will cause some evolution in the central star or source. And then what it will do is we'll have these different paths as it's shown here on the right for different masses of the particle. So then what you observe is essentially that it will start migrating outside of the soliton. And then depending on the mass, dynamical friction can bring it down, bring it back, I guess, to the soliton if it becomes too massive. So a few times 10 to the 7, which is basically I think it's 10% of the soliton mass, you can see that it will be trapped within the soliton. But as you go to smaller masses, then these systems can actually go outside of the soliton and be heated up by these fluctuations. The other thing that we're looking at more specifically in terms of what will be the effect of the star formation and feedback on this soliton objects, it's still in a semi-analytical way because we don't have simulations yet for these type of analysis. But so one of the things that we're doing with Luna that also has graduated, she's gone to the perimeter, So one of the things that we found there, what we explored there, is just to mimic the effect of feedback. So essentially, you can think of this as you have a soliton, and then it will accrete gas, and we mimic that by increasing the gravitational potential during some time. And then at some point, we just expel all that gas at once. So kind of mimicking some, burst of supernova that just expel most of the gas. And then we actually ask the question, how the dark matter will evolve after the blowout. So here, what is shown on the left is the central density for the soliton versus time. And you can see these different stages. So at some point, you increase the density because we're accreting this in this accretion phase. And then we expel most of the gas at once, which is this big burst, or gas where gas is blown out. And then what you observe later is this lingering oscillation of the soliton. And when you translate that to the density profile, or in this case to the circular velocity, what you end up having is essentially that you will have at different times, you're going to have solitons that are at different stages because it's oscillating. So what that means is that you're going to have some scatter on the circular velocity. And each of these stars that are shown here are individual galaxies that are in the field. So these are galaxies that are not in the tidal field of Milky Way, but they are still in the local group. And what you find is essentially that they kind of lie within the scatter due to, again, these sort of feedback effects. So this is quite encouraging because it means like even without, very being quite specific on the details of what the feedback is or how it affects, we're just saying, what is the total or net effect gravitationally, and we are already putting this model within, let's say, the observational, within the observations. So, of course, we want to do self-consistent simulations to understand how the gas and dark matter evolves in this model. And one of the attempts to do this is with this type of simulations that are mostly cosmological. And this is also at high redshift. This is not, unfortunately, at low redshift. But you can already see very big differences. And one of them here, that is shown here, you can see on the top is the cold dark matter. It's a typical cold dark matter simulation where you have a lot of structure. And then what we're showing here is essentially zooming of this yellow rectangle. And you can see the dark matter as it clumps. And you can see that the gas and stars, they basically will follow the dark matter, and mostly in the structures that have viralized. This is just the right, this is a slice of these zooming region. If you go to the fuzzy dark matter or scalar dark matter, what you observe is basically you still have these bigger halos. But one of the things that is quite different is that in dark matter, you form these dark matter filaments. And if you look at the gas and stars, then they actually cluster also within the filaments. And then most of the stars, well, a fraction of the stars also forms within the filaments, as opposed to the dark matter and cold dark matter case, where they actually cluster only in the, or mostly in the cold, on the viralized structures. And if you do a slice of these box, what you observe is, again, this very characteristic interference patterns, which comes from this quantum-like nature of this field. So it's quite interesting because even if you, well, I'm going to skip this one, but if you do the analysis of how these early galaxies form, then you can see that in cold dark matter, as you may expect, structures start forming quite early and then starts forming those structures. So by the time that you say you end up, redshift 6 or so, when neutralization is happening, then you already have some structures that are well formed and so on. Now, in this scalar field dark matter, because you have this quantum pressure, so then your dark matter will have some delay in this formation. Well, one of the things that is shown in this self-consistent simulations is that you actually start forming stars, even though the dark matter hasn't really fully visualized. And then once you start forming, let's say, visualizing your dark matter halo, you already have some fraction of stars in these systems. But you also have a number of stars, as it's shown here, in the filaments. So with time, those stars are actually going to be accreted into the dark matter halo. And by some, redshift, say in this simulation, redshift 6.2, you already have a very similar galaxy looking within only the viralized halo. But what is really different from this type of models is that you actually have a rapid formation of a system as opposed to something that goes more gradually. So this type of, how fast and how, rapid these early galaxies form could be another constraint that will be quite informative, specifically because now we're going to have observations with James Webb and these high redshifts. And again, one of the hopes of doing this analysis that we have to be careful is that it could be, biased towards like what in the universe we're looking at. It could be some region that is, very dense, or maybe we're kind of looking at a void and so on. So as these sort of authors have done in the quite early, well, back in 2016 or so. So this is kind of analysis that we want to pursue, in which we take different parts of the universe and then see what would be the bias by, the dark matter density field, if it's a, an over density region or under dense region. And so in order to gain statistics, we actually need bigger volumes in cosmological simulations. So this is, of course, way demanding in this type of dark matter models, as I showed, because of the interference patterns that you need to resolve. But this is one of the attempts that where Simon and Volker have been will have a simulation with the same code that I just showed at the beginning. And this is actually a bigger volume, but of course, this only goes all the way to redshift 3, which is still not redshift 0, but this is, again, pretty nice for doing analysis and statistical analysis. And you already see here there are different halos, and you can see how the solitron also is developing in the systems. So just to conclude, I think there's a lot of observations that are going to be telling us much more about dark matter in the next couple of years. And in particular, I mentioned the James Webb Space Telescope telling us information about the early universe, but also about the local universe. In particular, we're going to look at observations of the Rubin telescope. And one of the things that we would like to know is not only, as I say, things that are in the local volume and the internal structure of galaxies, but also how these same constraints can operate on early stages of the universe. And yeah, so finally, I just want to say that the dark matter physics is actually quite interesting because we can do a lot of constraining with the current observations, but we'll be hopefully we'll be doing much more in the next decade. In particular, we've already found that just with structure of galaxies in the Milky Way, there are some tight constraints on the cross sections for self-interacting dark matter that puts it in a very tight regime. And then in the scalar field dark matter, we already are putting some strong constraints in terms of what is the solitron sizes and what is the spectrum density slopes for those. So yeah, thank you.
Okay, thank you,
Yeah.
Victor. So any questions from the room, Marcus?
I have a bunch of questions, so I'll maybe find you later for some of them. But so one of my questions was, you showed these warm dark matter cutoffs, so I've been running simulations with interacting, but no longer interacting dark matter, essentially. And what I find is that even though the power spectrum has a strong cutoff at linear level, once you start running the nonlinear simulations, you get closer and closer to the cold dark matter level. So you don't actually, I don't see this super strong cutoff, but except initially, and then it maybe goes towards more flat profile in the Halo mass. Is that different from dark matter, or?
So yes, I think that's yeah. I mean, so you're talking about self-interacting.
No, so what I've been doing is dark matter that's coupled to relativistic species in the early universe, so you get diffusion damping in linear regime, and then but it turns off at like 75,000, so you don't really need to count for it other emissions.
Well, I mean, what I can tell you is yes, like when you do this type of hybrid or like different, dark matter physics that is now coupled to something that is relativistic and plus some other effects, then the type of spectrum that I showed here could change. That's for sure. The other thing is, like, even if you didn't do this hybrid models, just like even with dark matter, warm dark matter, or even the scalar field dark matter that I showed, is like these rollups that I showed, like you said, these are like linear approximations in that sense. So when we actually run the nonlinear simulations, in fact, I just forgot to mention, but well, we actually can't find objects that are below this Ginsey scale, right? So of course that is important because it means, like, as I said, the cutoffs are not as sharp or used to be taken as, like the ultimate answer. You actually have to run simulations to see, how much they are, how much of the nonlinear structure could affect this low end of the spectrum. Yeah.
Anyone else in the room? Sorry, hand it over. Well, I'll let Tony ask. So Tony has signed up. Do you want to go ahead, Tony?
Sorry, are you asking me to go?
Yeah.
Yeah, I got two simple questions. One, to what extent does an admixture of warm and cold dark matter help with some of these tensions?
So to what extent warm dark matter solves this? Well,
Leaving it's a mixture of warm and cold.
okay.
I mean, multi-phase dark matter where it's not, you have some hot and some cold.
Okay. Well, I mean, I think like it depends a little bit on the scale that you're thinking on where the cutoff, well, is sort of, transition from cold, or what fraction of cold to hot you're putting. Of course, you can always try to match, a certain fraction of cold dark matter so as to avoid the steep cutoff, for instance, for that I mentioned for 1 kV or so. Now the question there, I think it becomes a little bit more of the degeneracy that you can get, for instance, from just utter astrophysics. So it is possible. I think like that's a short answer. It is possible to find models in which you have this hybrid hot plus cold dark matter, but it becomes a little bit more challenging than to discard or to disentangle what comes, what observations or the constraints from observations are for dark matter, or is it they just baryonic physics acting at that scale. So I guess like you can put some upper bounds.
I just heard that it could help with the cusp core problem a little bit, but you don't want to wash out the fine structure completely, right?
Yeah.
So the other question was around the self-interacting dark matter. I thought one could infer fairly strong constraints on that from looking at the bullet cluster and the simplest interpretation.
Yeah, so that's a great question. Actually, we're just talking about it. So one of the things that happens in clusters is, yes, like there is some preference for low cross sections. So what I've just shown here in all this dark matter, self-interacting dark matter, is essentially a constant cross section dark matter. So that means there's no velocity dependence. And so if you take those constraints into account, and even though there's been some debate because some papers may actually quote higher numbers, in general, they will try to point out, or they will point out to something that is more velocity dependent. And I think in that sense, it is a little bit more consistent, let's say, from particle physics side. So there's some models that, can actually reproduce this or can give you this velocity dependence. And in the sense that actually will help a little bit in the, in terms of what I mentioned of this core collapse in dwarf galaxies. So it is true that this is still, constraining that you cannot have very large cross sections at the scale of galaxies, cluster of galaxies. But this is something that can be accommodated in the self-interacting dark matter scenarios.
So you're saying that the velocity dependent cross section might save you there?
Yeah, exactly.
Okay, thanks.
So yeah, Bruce, go ahead.
Questions about stop. So you showed early into this plot the number of satellites in the Milky Way known as a function of time.
Oh, let me go back to IT one. Yeah. Oh, it's gonna be hard to do it here.
So
Sorry.
you're right. I understand that there aren't enough satellites. But I guess what I don't understand is how well do you know
Yeah.
how few satellites there are? Because it's not, because if you don't introduce dark matter properties from them, in simulations, it's not enough to say, well, I don't think there are enough satellites. You have to be able to swear on top of this, look at real that there aren't enough satellites. There's nothing you can do to make the satellite go above. I just don't have a feel about strong knowledge.
See,
Do we really need to wait for the ruling?
Oh.
To answer that, or what's the?
Can you just briefly?
Yeah,
summarize
I could
questions
try.
for the
Yeah, let me
benefit
just
of
try
Zoom?
to.
Can you repeat the question, please?
Yeah, they would have.
I don't know if I can skip it. So the question is like, well, let me just try to understand the question. So the question was, observational, right? It's like, is how well constrained is the number of suspected satellites or small satellites that we should observe? Okay. So I guess I'll have to stop sharing, and then let me just share again. I just missed the flyer. I don't know what it is. Here it is. Okay, and then I'll have to share it again. Okay. Yeah. So as you can see here, yeah, like you're saying, there's this bunch of satellites being found and so on. So here's the thing, right? So we think there is some cutoff in the what is the number, below a certain mass that you cannot form stars. So then we think that there might be a cutoff just from the astrophysics side. So in that sense, then it is suspected that you don't see, things that are quite faint. So like anything that's below, I don't know, just to put a number, it could be like, a few thousand stars or so. But that depends on where these galaxies were living in when they formed, right? And that is less known, and that's where the dark matter part comes from, right? So like, what was the halo mass in which these galaxies formed? So in another sense, well, the way that people have put numbers for these to have a sense of like if we're complete or not, you can do like sky corrections. You can think of these as, we have some patch of the skies that we have covered, and then there are some others that we haven't. So if there is some numbers galaxies that are in this area that we haven't covered, modulo what we already found in the current survey areas, then you can somehow give a cap of like, this is the total number of structure that we can find if if this sky corrections are correct. Like, but of course the thing is that we don't quite have the very good sense of that number, because again, you can think of back in 2000, you can do these sky corrections if you want, and maybe the numbers would have been different from what we know now. So this is still like some problem, well, not problem, but this is just still quite uncertain. So we can know there's only some modular, sky corrections, a factor of 3 or so, but that's still not going to put you in like the hundreds. So I think the one of the things that from dark matter that we know is that we don't really expect like the same amount of structures in dark matter structures as galaxies. That's for sure, because there's always going to be very faint dark matter structures that shouldn't have any galaxy. So in that sense, I think that is what we can do about dark matter. And if in this sort of dark matter models that have cutoffs in the numbers of structures, those are more constraining, because again, you can already see that if you start finding more, even with sky corrections or whatever, then if you don't even have abundance of those objects, then it becomes a problem, because then you have like free floating galaxies without dark matter. Yes, it's more in the lower bound of the same that we also.
So we have a question from Geraint. So Geraint, I think you were first. You want to read out your question, or I can do it?
Yeah, sorry, a bit of a noisy background there. So there are other tensions to do with the distributions of satellites, in particular planes of satellites. Has this approach got anything to say about those?
Yeah. Okay. Well, so that's a little bit debatable, but that's yeah, that's a hard problem in the sense that there is, I mean, depends on who you ask here. So some people, I'm going to tell you just the agnostic position from an agnostic point of view. So there is certainly some tension on the fact that there seems to be a trend for the current galaxies that we observe in being in a plane, right? And there's also this sort of plane of galaxies for Andromeda, and there's also, if I'm not mistaken, there's also some of these type of orientations for another galaxy that's Centaurus, okay, if I'm not mistaken. So it's the issue here is like it's still a low number population to consider. This is a well, some people will say this is still just a few systems, and we don't know if this is just a random chance in which you find the systems to be aligning in this plane because they are still evolving and so on. So I think it's going to be hard to tell where this is a problem or not. But certainly, if you just only look at the distribution of galaxies as they are and the precession velocities, I think if you compare this with the cosmological simulations, cold dark matter simulations, at least, it's true that it's hard. It's within, let's say, the statistical sample, but it's not in the mean. That's for sure. So it's still possible, but it could be rare. Yeah.
Good.
All right, I'll allow one more question from Mikhail, and then we can finish. Mikhail.
Sorry, was that me?
Yeah.
Okay. Yeah, thanks for a great talk. I'm not really an expert, but we had a colloquium by Volker Springer in a few months ago, and you mentioned at the beginning of your talk that this field is very much debated, and the effects of ordinary matter on the form of the halo, and in particular the role of black holes that can also be simulated. Can you maybe comment on that a bit more? Probably the majority of your predictions for cold dark matter were without these new developments, I guess, right?
I'm not sure I understand the question. Is you mean like in terms of the black hole? Did that?
No, I mean the cold dark matter simulations and the effects of ordinary matter on the form of the halo that you mentioned at the beginning, at the special role, for example, of black holes that they could play. Can you maybe comment on that a bit more? That was one of your earlier slides.
Is that, you mean like the Corey cusp? Is that, maybe that's what you, correct me if I'm wrong.
Yes, right, the Corey cusp problem, right.
Okay. Yeah, okay. So I guess maybe I should.
With this one, right? No, yeah, this one, right?
Oh, okay. Oh, well. I mean, I think like so yeah, I mean, as I said, like this is a whole approach. So there's a lot of people working on what this type of solution, let's call it, we can get with the astrophysics. So it is, as I mentioned, like there are some of these discrepancies that can be ameliorated with or can be minimized, let's say, with some sort of stellar physics. But the issue that has always been lingering on the stellar physics side is, that of course you have to make sure that you can cover basically all these regimes, right? So you can tune your physics, let's say, to match, I don't know, dwarf galaxies, for instance. But then what you have to do is to make sure that that is not inconsistent, let's say, for what you will expect for a Milky Way, and on our different scales. So I think that the play, where the game in all the stellar physics side is that you can recover some for close transformation if you have, again, this law of feedback and whatnot. But then the question is how much of the galaxy that you simulate actually looks like real galaxies. So sometimes it could be that your galaxies are just too puffy because you just have too much feedback, or it could be that you have a lot of metals. So there are these things that you can always have knobs to play, and I think that this is kind of part of the exploration of like how galaxies basically form, or how you even form stars from the gas. So certainly there is some approach. I mean, this approach has its successes, of course. I think that is a different solution, but I think that there's still work to do, and that's, I think, why people keep running a lot of simulations on this side. Yeah.
Okay, thanks.
All right. So I think because we're going over 5 p.m., I think I'll call it a day there. So thank you very much, Victor, and yeah, let's give it another round of applause. Thank you.